All right, number 8 says that we're supposed to find a counterexample. And the counterexample goes with, I'm just going to take a picture. And then I'll just erase my answer. That ain't going to help. All right, just so we're all looking at the same thing in case we don't have ours. So pretend I don't know the answer. Now, if I ask for a counterexample, I'm not trying to trick you. So on the test, if I say there's a counterexample, there is at least one counterexample. And if I was asking this in a more official capacity, I probably wouldn't pick these hard ones. But in order to have a counterexample, we have to remember that this part needs to remain true. So whatever n value I pick, that part has to be true. To be a counterexample, this part needs to be true, but this part needs to be false. So the first part needs to be true, the second part needs to be false. So if I would pick n equals 5, I'd have 5 squared, 25 equals 5 times 5, 25. This part would be true, but so would this part. So that's not a counterexample. That wouldn't work. If I pick something like n equals, let's say 6. 6 times 6 is 36. 5 times 6 is 30. Is 36 equal to 30? That can't be a counterexample because this first part must be true. Now, here's a bit of advice for you for counterexamples, particularly with algebra. If you can't find one, that means your counterexample is probably either 0 or uses negative numbers. Those are the things that break algebra, zeros or negative numbers. So my first shot is, let's try 0, and then I'll try negative numbers. So let's try n equals 0. Does 0, what's 0 squared? 0. What's 5 times 0? Is 0 equals 0? So that first part's true. Is 0 equal to 5? No. So that's my counterexample. That makes that first part true, but that second part is false. So I would just circle that and say, yep, that's my counterexample. First part true, second part false. Does that make a little more sense? All right, cool. What else we got? I don't know what's happening over there. 15 and 16. 15 says, rewrite each pair of conditionals as a biconditional. Let's replay kind of our note section really, really quick. So in our notes, I don't know why I flipped the wrong way. Let's go that way. Oh, that's going to be upside down. I got this. So our note said that if I have a conditional or another statement, I need to write it as a biconditional. We have to locate a hypothesis and a conclusion. Then all we have to do is connect them with the words if and only if. That's our one thing. Now we pick a hypothesis and a conclusion. We can find it by the words if and only if. And it doesn't matter what order you put them in. I could have written this as x equals 5 if and only if x 4x equals 20. So keeping that in mind, if I look at, we're doing 15 and 16. If I look at 15, 15 says if B is between A and C, then AB plus BC equals AC. And then the next one says AB plus BC equals AC, then B is between those two. Let's take a quick picture, and let's see what I did. So all I did is I took the first hypothesis, and I rewrote it without the if. Then I joined that, so that came from there. Then I put if and only if. And then I took my conclusion and put it at the end because I can say it in either direction. If and only if allows me to say it in any direction I want. Both could be the hypothesis or the conclusion, and it would be a true statement. So this basically is a way to rewrite two true statements that are converses of each other as one big statement. Does that help you with 16 then? Don't overthink it. Bless you. Measure of angle, yep. Yeah, angle AOC. Just don't forget those terms. So that's measure of angle AOC. And the other one says angle AOC. All right, other questions? 6. 6 says a counterexample shows that a conjecture is false. We need to write that as an if-then statement, right?
Yes.
So what I would kind of think about, I'm going to take a picture and I'll kind of talk you through my thought of this. We have two things happening. We first must have a counterexample, so I'm going to stop reading there because that's one big thing. And then we have showing a conjecture is false. Those are my two big statements. I have a counterexample, which will show that the conjecture is false. So I don't want to write this as if counterexample, then show that conjecture is false. We just have to make it a little bit more eloquent. So what I said is, if it is a counterexample, or if there is a counterexample, or if you have a counterexample. So I have if it is a counterexample, then it shows that a conjecture is false. Or you could say if it is a counterexample, then the conjecture is false. Something along those lines. So the hard part is we should get the if and then part kind of right. It's just making it kind of make more sense in an English classroom kind of thing. And I'm not looking for perfect sentences. I just want to look that you actually tried to rewrite it in a proper way. All right. Anything else? Yeah. Yeah. Lavente. Okay, 20 says, if angle POQ is a straight angle and R is a point not on PQ, then something plus something equals something. So this is kind of a review from Unit 1 of sorts. So if I kind of take an example of this, I try to draw the picture as best I could. So I know I didn't give you a ton of room to do that, but if I was given something like this, I would see what picture would make sense to me. So I know we have POQ is a straight angle. Now, a straight angle to me means it makes a line. So straight angle to me means it's a line. So that's what I did. I drew POQ, or PO, should have did Q here, huh? Let's change that to Q. This is that straight angle that we had here. Then it says R is any point not on PQ. So I just drew a point above it. It just can't be collinear with it, so it's just above it. A point not on PQ. Then, well, we had to realize that it's talking about angles. So what I did, Elmer, is I realized that we're talking about angles, so I should probably connect this to start forming some angles. And then I could see, oh, you know what? They're just asking about the angle addition postulate. The angle addition postulate says, well, one angle plus another angle equals the big angle. And so I just said, POR is ROQ. This should be a Q. That could have been confusing too. This should have been a Q as well. And that must equal 180. You could say it equals the whole line, but a line equals 180, so this is the best way to answer that. Does that make a little more sense? These can be tough, especially when they don't say it forms an angle. They're just like there's a point above it. My advice is always just draw it. And that way, if I can't get it, at least I understand parts of it. And I can show that little bit of understanding. Anything else real quick? Good? Bueno? Done with conditionals? Okay. Then we're going to move on to something a little bit different. A little more of a step up. We're going to go up to deductive reasoning. Oh, I got to go all the way back here. Deductive reasoning is just a process of reasoning. It's kind of like an if-then statement that we can deduce that something happened or didn't happen. So it is a process of reasoning using given and previously known facts to reach a logical conclusion. Law. If a hypothesis of a true conditional is true, then the conclusion is also true. So if I give you a true statement, I say something like, if angle 1 is 13 degrees, then angle 1 is acute. Is that a true statement? Yes, any 13-degree angle has to be acute, so that's a true statement. So what this is saying is, now I actually give you a 13-degree angle. You could then conclude that it is, in fact, acute. So if it's a true statement, and you actually get the first part true, then the second part will follow. Or if I say, on Unit 2, if I study for the Unit 2 test, I'll do well on it. Then in the future, all of a sudden I get to the test and I studied for it. That means logically I should do well on it. That's the logic of it. Basically, we hypothesized something happened. Now we're actually going to give it to you. What can we conclude if that happened? All right. So that is kind of the law of detachment. And we'll get to that in a second. So the law of detachment is a law of logic that states if a conditional statement and its hypothesis are true, then the conclusion is also true. So we have two big words today. Law of detachment. You want to get it? We'll just get to it later. But syllogism is the second part of it. So we have law of detachment and syllogism, but we'll see that in a second. So let's just talk about law of detachment. Law of detachment says, if your hypothesis is true, then your conclusion must also be true. So in these three examples, it says, what can you conclude from the given statements? Label the hypothesis and conclusion. Do we have a lot of room to label everything? Like, do we want to write those full sentences out? Probably not. So let's speed up how we can note our hypothesis and conclusion. So I'm just going to box in that statement that's after if. Is that first statement your hypothesis or your conclusion? That's my hypothesis. So I'm going to smack a P up there. In your backpack. Then I'll just highlight the second part. It's actually that whole thing. That is my conclusion. So this says, if a student gets an A on a final, then the student will pass the course. Is that true? If you get an A in a class, do you pass that class? Yeah. I mean, we can do some other things but if you get an A at the end of the year, they're not going to say you failed this class. That wouldn't make sense. So if you get an A in a class, you pass that class. So that is a true statement. So then it says Matt got an A on his history final exam. What does that mean for Matt? That he passed. Because this makes the hypothesis true. That makes the hypothesis true. So that statement makes hypothesis true, makes P true. So that's going to lead us to the conclusion. So we can conclude that Matt passes the course. Or Matt passes, I guess we could say history. So if there's a concrete example that makes the hypothesis true, then the conclusion will follow for them. That's the law of detachment. That we're detaching these two statements, we're making it true, and we're seeing if the other part is true too. So our next thing says, if two angles are adjacent, then they share a common vertex. If two angles are adjacent, do they have to share a vertex? Yes. Yeah, that's the definition of being adjacent. Adjacent, the first thing we said was they share a vertex and a ray. So if you are adjacent angle, then you must have a common vertex. So this is a true statement. We should go ahead and follow directions because it says mark your hypothesis. That's my P. My Q would be they share a common vertex. That's my Q. Angle 1 and angle 2 share a common vertex. Does that prove that the hypothesis is true? Read the hypothesis. The hypothesis says two angles are adjacent. Does my fact say angle 1 and angle 2 are adjacent? Does it directly say that? It says angle 1 and angle 2 share a common vertex. Is that the hypothesis or conclusion that I'm stating there? That's the conclusion. The law of detachment says the first part has to be true. That will let the second part be true. It doesn't work backwards. If-then statements go in one direction. So what can we conclude from this? Actually, nothing. So I'll put here, this matches the conclusion. But it does not match the hypothesis. No conclusion can be made. No conclusion can be made because the law of detachment says the hypothesis has to be true. Not the conclusion, but the hypothesis needs to be true. All right, C says, if a ray divides an angle into two congruent angles. Do you see why it's important that we should locate our hypothesis? We have to know what our hypothesis is to see if the statement proves it true or not. So that's my P. My Q would be the ray is an angle bisector. Okay, our hypothesis is a ray divides an angle into two congruent angles. Our conclusion is that ray is an angle bisector. The statement says RS divides angle ARB so that ARS is congruent to angle SRB. Is that our hypothesis? So our hypothesis says if a ray divides an angle into two congruent angles. Does RS divide an angle into two congruent angles? Yeah, it actually says it. It says RS divides an angle into two congruent angles. It tells you the two congruent angles. So this proves the hypothesis true, right? So this would match the hypothesis. Matching the hypothesis says we can use the law of detachment to say then the final thing is true. So this actually matches our hypothesis. Matches the hypothesis. So can we conclude something? What can we conclude? Yeah, we just got to fill RS in for this blank ray because it just says the ray. In this case, our ray is RS. So our conclusion is RS is an angle bisector. So sometimes we can straight up use the words they use, but other times we're going to be given letters and stuff that we're going to have to supplant instead of just saying the ray. That is the law of detachment. The law of detachment leads to the law of syllogism. Syllogism is a whole train of if-then statements. It's a whole train of if-then statements. If we have time, we'll play a video on that. So it's a whole train of if-then statements. So it might be, if I attend class, then I will increase my grade. If I increase my grade, I will do better in the class. If I do better in the class, then I will pass this class. If I pass this class, I will pass next year's class. If I pass next year's class, I'll keep passing classes. And if all that happens, then I graduate and go to college. It's a chain of if-then statements that follow the statement before it. So there has to be some link between the two. It can't be, if I teach this class, then I'm going to go to the game tonight. Is there any link between me teaching this class and me going to a game tonight? No, not directly. We'd have to have some kind of thing. So it might be, if I teach this class, then I get paid. If I get paid, then I can pay for the game I have to go to tonight. There has to be something that connects every single statement. Kane, is that okay? So there has to be something that connects it. So the way we're going to connect these is the conclusion of your first statement has to connect to the hypothesis of your follow-up statement. So real quick. So law of syllogism. If P, then Q. If Q happens, then R happens, which would tell you if the first thing happens, then that last thing happens as well. That they all is like dominoes. Think of it as dominoes falling. That if I hit the first domino, the next domino falls over. If that domino falls over, the next one falls over. So if you hit that first one, they all are going to fall over, so you can conclude that they all fall over. My example here is if it is July, then you are on summer vacation. If you were on summer vacation, then you work at a smoothie shop. This might not be you. If you work at a smoothie shop, then this is the example for you. If not, just pretend you work at a smoothie shop over the summer. So what can you conclude? Well, if it's July, I must work at a smoothie shop because I can connect those two statements together, that they have to fall like dominoes. All right, so let's do some examples. So it says, allow you to state the, so the syllogism allows you to state the conclusion from two true conditional statements or more. Two or more, I should have put that in there. When the conclusion of one starts in the hypothesis, when the conclusion of one starts with the hypothesis of the other statement. So we have, if a figure is square, then the figure is a rectangle. This has to link to the next statement to be the law of syllogism. So our next statement says, if a figure is a rectangle. These link together. They link together. Because this ends where this one begins. Then the figure has four sides. So if a figure is square, then the figure is a rectangle. I think I missed something. So what you can conclude from this information is we can shorten this. We can put, if a figure is a square, we can skip the whole rectangle thing and go to, then the figure has four sides. So the law of syllogism allows you to skip that middle section. Like I said, if I hit one domino over, it all falls over. I don't have to say, well, domino 2 falls over, domino 3 falls over, domino 4 falls over. I can say the whole thing happens. So as long as you can keep hooking that stuff up, you can skip everything in the middle and just start and end at your final conclusion. If you do gymnastics, then you are flexible. If you do ballet, then you are flexible. This is our conclusion that needs to link to the next statement, right? So in the law of syllogism, it says you have to take the conclusion of your first statement to connect it to the second statement. Does that connect to you do ballet, you are flexible? No, this is hooking up a conclusion with a conclusion. That's not how law of syllogism works. Just because they use the same words, it's in the wrong order. It doesn't match up with the hypothesis. So basically, if I try to go from here to here, that doesn't work. That doesn't line up. That doesn't work. These are not the same. So that means we can't make a conclusion. No conclusion can be made. I feel like these problems can sometimes be the most confusing because you're like, the same words match up, so it must be law of syllogism. Make sure you're asking yourself, what's the conclusion of one? What's the hypothesis of the other one? I think we're on the next page. And we should probably, yep. All right, C says, if a whole number ends in 0, then it's divisible by 10. So if I'm looking for the law of syllogism, I'm looking at the conclusion. If a whole number is divisible by 10, well, is that the exact same wordage? Not exactly the same, but does it mean the same thing?
Yes.
It is divisible by 10 if a whole number is divisible by 10. So it doesn't have to be exactly the same words, but as long as it means the same thing, they are going to hook up. So these actually match up. This is good. This is good. This matches. So if a whole number is divisible, ends in 0, then it's divisible by 10. If a whole number is divisible by 10, then it's divisible by 5. What can I rewrite these two statements as? Ooh, boy. Joseph. Okay. Someone had to start, right? If a whole number ends in 0, then it is divisible by 5. If a whole number ends in 0, then it's divisible by 5 by the law of syllogism. See about this one. On your own, to decide if this can use the law of syllogism. I'm going to put this back up because I see people still taking notes on it. Do the next one. If it's law of syllogism, we need to come up with a new statement, conclusion. If it's not, just put no conclusion can be made because there's no link between the two. I usually have backup lessons. If you ever forget, it doesn't pay to switch over now. But I assume you're just going to put that on. Yeah. As long as you're in a camp, that's what I love. All right, so it says if AB and AD are opposite rays, so they're both rays, then the two rays form a straight angle. Now remember, our job is to look at the next hypothesis. The next hypothesis is two rays are opposite rays. Does this say opposite rays?
No.
Guys, you okay? Okay. Does this say if two rays are opposite rays? Are they close?
Yeah.
They're close, so I could see why we thought it was syllogism, but it has to be exactly the same. Like, it has to say straight angle. So this would not be syllogism. These do not connect. So no conclusion. Does that make sense why there's no conclusion can be made? Let's put that in our backpack. Okay, then the last thing is we're going to combine the two things together using the law of syllogism and detachment. Now we're going to be given a statement. We're going to see if we can combine them, and we're going to see if the statement that they provide allows us to figure anything out. So this says, if you are climbing a mountain at an altitude of 28,500 feet or higher, then you are on the tallest mountain above sea level on Earth. If you are on the tallest mountain above sea level on Earth, then you are on Mount Everest. Does this conclusion match up with this hypothesis? Okay, so you're telling me that this one ends in kind of tallest mountain above sea level on Earth. You're saying that's how the hypothesis looks like on the next one? Yeah, be confident. Yeah, you're right. It links up with you are on the tallest mountain above sea level on Earth. Tallest mountain above sea level on Earth. Tallest mountain above sea level on Earth. I don't know how much closer they're going to get than that. So law of syllogism says I can combine those two statements. So now it says Jude is climbing at an altitude of 29,000 feet. What can we conclude about Jude? Owen? He's on the tallest mountain on Earth. So we get to that one, which links up to this statement, which we can go further and then say he must be on Mount Everest. So you are correct to conclude this, but law of syllogism says we can then connect it to this one as well. So Jude is on Mount Everest. Oh, does that make sense how you can do that additional step? Okay, our next one says, if a river is more than 4,000 miles long, then it is longer than the Amazon. If a river is longer than the Amazon, then it is longer than, and then it's the longest river in the world. So let's first see if we can connect it through the law of syllogism. Does the conclusion of the first sentence match the hypothesis of our first sentence? Daniel, what do you think? Just say yes. Yeah, he's got it. Even sleeping, he got it. Can someone explain to me why I could say, yes, I can connect it to the law of syllogism? What statement am I looking at that connects the two? Santiago.
Like the distance?
What is... Oh, yeah, it tells. Do you know what words I was looking for?
Longer?
Longer than... And we're going to pick all of them.
Longer than the Amazon?
Longer than the Amazon. Kind of. So if a river is more than 4,000 miles, then it's longer than the Amazon. And then we're going to see longer than the Amazon on the hypothesis here. So I didn't ask a very clear question. So that's how it connects those two things. Yeah. Yeah. So now they're telling us that the Nile is 4,000... Well, if you do it quietly... the Nile is 4,132 miles long. What can I immediately say after that? Shh. Let people think about it. We'll go other Joseph. Yeah. Then it is the longest river in the world. So the Nile is 4,132 miles. It's definitely longer than 4,000, which means it's longer than the Amazon. Longer than the Amazon means it's the longest river in the world. So the Nile is the longest river in the world. Probably put river. All right, that's the law of syllogism with the law of detachment. In example 3, does it matter whether you use the law of syllogism or the law of detachment first? Explain. Which one did we have to use first, Owen? Yeah, give me 1 second. I'm going to finish this statement, and then we'll go back. Ty? We'd have to use the law of syllogism first. I agree with that. Someone besides Ty, because I think he's got to explain why. It lets you match, because if they didn't match up, we couldn't use the law of detachment to get from one end to the other. That is correct. So we should have something along those lines. That syllogism must come first, so you can link it up. Otherwise, the law of detachment can't get you to the end. Now let's go over the question on law of detachment. Otherwise, that's the end of our lesson. So if you want to start working on your homework, you can. If you want another explanation on the law of detachment, we'll go over that real quick. No Alex assignment, just the paper. Sorry, yeah, so it'll be the front and back of that one. I will look at it once I finish answering your question, okay? So that means I'm still talking, but you guys can work as long as you work silently. As soon as I'm done, I'll let you know. All right, law of detachment for one more time. Law of detachment says, if you have an if-then statement, and then something happens to make the hypothesis true, it leads to the conclusion also being true. So if you read the statement, if a student gets an A on a final, then the student will pass the course. This is just an if-then statement, hypothetical. All of a sudden, Matt actually gets an A on his history final. That means he will pass the course. So I can jump to the pass the course. So I can use my first hypothesis to end with the conclusion. Now if it's concrete and Matt gets an A, that means he passed the course. That's why we came up with our hypothesis inclusion for all of these. But you just have to be clear, Owen, that sometimes I try to trick you. So our hypothesis was if two angles are adjacent, then it says angle 1 and angle 2 share a common vertex. That's not the hypothesis, so I can't conclude anything.
The hypothesis is if two angles are adjacent.
Yep, so if this said angle 1 and angle 2 were adjacent, then we could have went further and said, oh, they must share a common vertex. But this has nothing to do with the hypothesis, so there's nothing I can conclude then.
I thought adjacent angles do share a common.
They do, but note that this specifically says angle 1 and angle 2 share a common vertex, but it doesn't say they're adjacent. Law of detachment only says that if the hypothesis is proven true, then the conclusion is also true. And this one says if two angles are adjacent, so if I was looking for law of detachment, this must say something about adjacent. Does this say anything about adjacent? No, so law of detachment won't work. Yep. It's close because it's got same wordage, but it's not the hypothesis.